Hello everyone. In this tutorial, we will look at some questions to help you to understand the calculation for extravascular administration. First, pause the video and try to solve the questions, and then play the video for my explanation. Let's begin. For this question, you need to use the data set on the right hand side to plot on a semi-log paper. By using the graph, and we can solve all the calculation and identify the parameter. Now you can pause the video to try to answer the questions. This is the graph you should get. We know that by calculating the gradient from this point to this point, you can calculate the elimination rate constant Ke. However, when you need to calculate the absorption rate constant Ka, you need to perform additional steps. First of all, you need to place your ruler and draw an extrapolated line. And then you need to identify the concentration here corresponding to this time point over here. We have another 3 points, 1, 2, 3. Doing the same thing, you need to identify the concentration for all the 3 points. With that, we need to do a subtraction. For example, this is A and B. You need to use A minus B to get another concentration. With that, we can draw another data set, and I will explain to you in the next slide. This is the data set after subtracting the value for the other 4 time points. This is the original value from the blood plasma profile, and this is the one for the extrapolated line. By subtracting this data set, you will find the differences over here. By plotting another line using this time point corresponding to this concentration difference, you will be able to find the gradient for this line, and that represents the absorption rate constant Ka. So let's take a look on the straight line in the next slide. This is the additional line you plotted to identify Ka. For the calculation of Ka, I'm using ln 22.1 minus ln 54 divided by 4 minus 0.5. With that, your answer is 0.26. And then for the Ke, starting from this point over here to this point, my calculation will be ln 2.5 minus ln 31.9 divided by the time frame 48 minus 8. With that, your answer for Ke will be 0.064. Okay, so we managed to find Ka and Ke. For question 3, you need to calculate the volume. Over here, we can use any time point corresponding to the concentration. Over here, I'm going to use time point number 12 after the peak concentration. You have to recall the equation for single dose administration. So first, you need to write down the equation, and then Ka minus Ke, E minus Ket minus Ekat. So the information is when T is equal to 12, the concentration is 28.2. So you need to put in all the value. The concentration is 28.2. Assuming the bioavailability and sort factor is 1 in this case, the dose is 5, volume unknown, 0.26 over 0.26 minus 0.064. So you have to be careful when you key in the value in the calculator. And the T is time point is 12, and Ka 0.26 multiplied by 12. So solve this calculation. The volume you should identify 9.9 liter. So that is for Part 3. For part 4, we need to calculate the T peak, the time to reach the peak concentration. So after a single dose administration, this is the time point when it will achieve the peak concentration. So we have another equation for the T peak, or we can call it T max. That will be Ka minus Ke ln in bracket Ka over Ke. So put in the value, that will be 0.26 minus 0.064 ln 0.26 over 0.064. You will find the value that will be 7.1. Now you found the T peak that will be 7.1 hour. So it means after an oral dose administration, it will require 7.1 hour for the concentration to climb to the maximum. So this is the Cmax, or we call it C peak. The equation is actually the same, but just let me write down again so you can follow my steps carefully. And E minus KET minus EKAT. Over here, you need to substitute the T using the 7.1. Now we calculate the concentration. 500 divided by 9.9, 0.26 minus 0.064 e power 0.064. So this is 7.1 minus EKAT, 7.1 as well. By calculating this, your answer will be 31.7. So this is the peak concentration, 31.7. That's all for this question. We will proceed to the next question. This question is for single dose extravascular administration. It's very much similar to the previous question, except the way they ask the question is slightly different. Now you can pause the video to attempt the questions. For question 1, you need to calculate the concentration at T equal to 4. Since the equation is given, C equal to 40, e power negative 0.15 t minus e power 0.62 t. You can substitute the value t equal to 4 to find the concentration. Just let me write down all the value. 40 e power negative 0.15 multiplied by 4 minus e power 0.62 multiplied by 4. Solve this equation, your answer will be 18.8 mg per liter. So this is the concentration when T is equal to 4. For second part, you need to calculate the half-life. If you look at this equation, FSD divided by volume, Ka minus Ke. This first part over here is equivalent to 40, while the second part, E equal to KET minus EKAT, the Ka and Ke is 0.15 and 0.62 respectively. So you can get the value for the T half equal to ln 2 divided by Ke. So the Ke is 0.15, 0.693 divided by 0.15. Your answer will be 4.6 hours. For third part of the question, you need to calculate the volume. Recall the equation. Ka minus Ke is equivalent to 40. Let me just put in all the value. The dose is 500. Volume. Ka is 0.62. 0.62 minus 0.15 equivalent to 40. Solve this and you will able to find the volume is 14.9 liter. The last part of the question, you need to calculate T peak and C peak. First, we identify the T peak. Recall the equation Ka minus Ke ln Ka minus over Ke. Just let me put in the value so you can follow closely. Minus 0.15 ln 0.62 divided by 0.15. The T peak you should get is 3 hours. And then write down the equation again. E minus 0.15 T minus E 0.62 T. Substitute the 3 into the equation. You can find the concentration will be 19.2 mg per liter. That's all for this question. For question 3 and 4, we will look at the calculation for multiple extravascular dosing. You can pause this video to attempt the questions. The first part of the question, you need to recommend the maintenance dose to achieve the CSS average of 10 mg per liter. Before that, you need to calculate the clearance. The K is 0.2, clearance unknown, and the volume is 24. Calculate the answer. The clearance will be 4.8 liter per hour. The equation for steady state average concentration will be SSD divided by CL tau. Over here, the bioavailability is 0.8, sort factor is 1, dose divided by clearance 4.8 multiplied by the interval 8 hours. The answer for the maintenance dose will be 480 mg. The next part of the question, you need to calculate the loading dose in order to achieve the steady state concentration of 10. The equation for the loading dose will be dL equal to dm 1 over e power ke tau. The concept of the loading dose is, let's say this is the steady state. You have the peak and then the trough. Somewhere here with the average is the CSS average concentration. The concept is you want a loading dose to hit the 10 mg per liter for loading dose. Now, using the maintenance dose of 480, 1 minus e power ket. The ke is 0.2, the interval is 8. Solving this equation, the loading dose recommended will be 601.5 mg for the loading dose. To calculate the concentration at time point number 4 during the steady state, you need to use the equation with the accumulation factor. First, write down the equation Ka minus Ke. Now, you need to be careful with the equation because you need to put in the accumulation factor. Over here is 1 minus Ka tau, and this will be 1 minus e ke tau. Right, let's put in all the value. There will be 480 multiplied by 0.8 divided by the volume is 24. Ka 0.5, 0.5 minus 0.2, then e power 0.2 multiplied by 4 because your time point is number 4. 1 minus e 0.2 multiplied by 8. So this is Ka 0.5 multiplied by 4. 1 minus 0.5 multiplied by 8. Okay, it's a very long equation, but you just have to be careful when you key into the calculator. The final answer you should get will be approximately 11.4 mg per liter. So that's all for question number 3. This is the last question for this tutorial. For this question, it is also involving the multiple extravascular administration. Now you can pause the video to attempt the questions. Before I show you the solution, let me explain a little bit about the T-peak SS. If a single administration is given, this is the profile, and that will be the T-peak. However, if multiple administration is given, slowly the concentration will climb and eventually we will hit the T-peak over here. But T-peak in this case is known as T-peak during the steady state. The equation will be different compared to the equation for a single dose T-peak. For the T-peak SS, the equation will be 1 over Ka minus Ke ln Ka and 1 minus E Ke tau. So be careful, this is Ke, and that will be Ke 1 minus E Ka tau. Now you need to put in all the value. Just let me write everything down. 0.8 minus 0.25 ln 0.8 0.25 1 minus 0.25 multiplied by the interval, which is 12. 1 minus 0.8 multiplied by 12. Right, so the final answer you should get will be approximately 2 hours. So it will take 2 hours for the concentration to climb up to the peak during the steady state. So let's move on for the next calculation. Once you identify the T-peak during the steady state concentration, the next thing is you can use this time point to calculate the C-peak during the steady state. First, recall the equation FSD divided by volume, Ka minus Ke, and E minus Ket. Over here, that will be the T-peak minus E Ka T-peak, and then the accumulation factor 1 minus E Ke tau 1 minus E power negative Ka tau, right? Okay. The next thing is you need to put in all the value. Just go slowly. 0.8 multiplied by 100 divided by 15. 0.8 0.8 minus 0.25. E negative 0.24 multiplied by 2. 1 minus 0.25 multiplied by 12. This is Ka 0.8 multiplied by 2. 1 minus 0.8 multiplied by 12. With that, the C-peak during the steady state is 3.39 mg per liter. To calculate the trough concentration, you will need to use this equation FSD divided by volume, Ka minus Ke, and then E power negative K tau 1 minus E power negative K tau. Over here I will remove the absorption portion because at this point over here at the trough the only parameter that take place will be elimination only. The absorption is completed, so you can remove the portion. Let me just write down all the value. That will be 0.8 multiplied by 100 divided by 15. 0.8 minus 0.25 e power 0.25 multiplied by 12. That is the trough time point. Y minus 0.25 multiplied by 12. By solving this, your answer will be 0.4 mg per liter. The next question is about the average steady state concentration. the CSS average will be FSD divided by CL tau. Before that, I need to calculate the clearance. So again, K equal to clearance divided by volume. So the clearance will be 0.25 multiplied by 15. Your answer should be 3.75 liter per hour. So put this value to the equation. That will be 0.8 multiplied by 100, 3.75 multiplied by 12. The average steady state concentration will be 1.78 mg per liter. The next thing I want to explain to you is about the steady state and the fluctuation. Let's say the interval is 12. You will have something like this. The interval will be 12. And for the interval 6 hours, what you will get is something like this. And in the roughly here, that will be the average. You will notice that the average will be similar except the fluctuation. Comparing 100 mg, 12 hourly, and 50 mg, 6 hourly. Remember, the higher the dose, the higher the interval, the longer the interval, the greater the fluctuation, because you are allowing more time for the body to clear off the drugs. And of course, if the dose and the interval is smaller and shorter, the fluctuation will be smaller. So that's all for our tutorial. Thank you for your attention.